Hey everyone, welcome to this explainer, brought to you by Forge College. If you've been following along in our From EVM to SVM track, you are in for a real treat today. We're continuing our architectural deep dive by tackling the absolute ultimate blueprint for understanding performance limits: state management. Today we're doing a complete overview of the state models in both the Ethereum virtual machine and the Solana virtual machine. So grab your hard hats and let's dive into the blueprints.
Here's what we're looking at today. First, what actually is blockchain state? Then, persistent versus ephemeral state. Next, we'll open up the EVM filing cabinet before heading over to the SVM locker room. We'll put them head-to-head in a token transfer showdown and wrap up with a summary and next steps.
All right, Section 1. What is blockchain state, the ultimate boss of performance? So remember our last lesson on performance trade-offs and runtime constraints? We talked a lot about gas limits in Ethereum and compute budgets in Sealevel, but why do they even exist in the first place? Well, reading and writing data across a whole distributed network it's honestly incredibly resource intensive. Those metering limits literally force us to be as efficient as possible with every transaction. But today, we're shifting our focus. We aren't just looking at the cost of those limits anymore, we are zooming in on the actual substrate those limits restrict, the state itself. Moving right into Section 2, persistent versus ephemeral state. What stays and what fades? Okay, we absolutely have to separate these two concepts right out of the gate. First, you've got persistent state. This is your canonical on-chain database. It survives block commits. When a transaction changes this state, you are permanently altering the blockchain. And guess what? Because of that, altering it costs real, painful money. On the flip side, we have ephemeral state. Think of this as the virtual machine's temporary scratchpad. Stuff like registers, the stack, local memory. You use it while the transaction is running, but the second it finishes, or if it happens to fail, poof, it just vanishes. You only pay that heavy premium for the persistent data that actually sticks around. Section 3. The EVM filing cabinet. Centralized and standardized. So in the EVM, the entire canonical persistent store is organized into one massive global index. It's called the global state trie, specifically a Merkle-Patricia trie. Every single account address out there maps back to this one giant centralized structure. And get this, a single root hash from this trie is used to verify the state of the entire network. It is incredibly standardized, meaning the virtual machine tells you exactly how your data has to be mapped out.
To really picture this, I want you to imagine a colossal, highly secure filing cabinet. Every smart contract, it's a locked drawer inside that centralized cabinet. And inside that drawer are these standardized, numbered compartments. Those are your 32-byte storage slots. Now picture a single, totally overworked, heavily sweating EVM clerk. When a transaction rolls in, this poor guy has to find the right drawer, unlock it, dig into a specific 32-byte compartment, change the number, and then update the master index for the entire cabinet. Because there's only one clerk and one cabinet, everything has to happen one at a time. It's highly consistent, sure, but man, is it a massive bottleneck.
Which brings us to Section 4, the SVM locker room, sprawling and decentralized. Let's step out of that stuffy, centralized office for a minute. Over in the Solana virtual machine, instead of one giant state tree, we use what are called program-owned accounts. These are basically discrete, independently sized blobs of binary data. The runtime does not force a strict 32-byte rule like the EVM does. Instead, the programs themselves act like external managers. The program actually owns the account, and it decides exactly how to interpret the bytes inside that blob. So we're talking about program-managed state rather than entity address state. And this leads us to my favorite metaphor, a massive, sprawling locker room. No more single filing cabinet. Imagine thousands and thousands of independent lockers spread across a giant warehouse facility. Each locker has its own totally unique key. And instead of one stressed-out clerk, imagine an absolute army of clerks zooming around the room all at once. Because the lockers are totally separate from each other, multiple clerks can do their jobs in parallel. The only catch? Two clerks just can't crash into each other trying to open the exact same locker at the exact same time. As long as they've got different keys, it's full speed ahead. So looking at this drafting board summary here, the EVM gives us per contract storage slots using 32-byte keys, all verified by that one global state trie, and that forces everything to be single-threaded. Solana, on the other hand, uses those independent blobs with program-managed offsets. There's no single massive trie for all the program data, and crucially, it allows parallel execution, just as long as the accounts don't overlap. It's honestly a beautiful architectural contrast. Section 5. Token Transfer Showdown. putting the models to work.
Let's take these abstract ideas and bring them down to earth with a real developer scenario. Say you want to transfer a token. In the EVM, an ERC20 contract stores all the user balances in a single mapping inside its drawer. To make a transfer, our EVM clerk has to do all this: read the sender slot, read the recipient slot, crunch the new math, write the new balances to the slots, and finally, update the global state trie. If 1,000 people are trading that token, they literally all have to stand in line and wait for that exact same drawer to open, one by one. Talk about a sequential traffic jam.
But check out the SVM flow. Here, the token program itself and the actual user balances are completely separate blobs. When you submit a transaction, you actually have to provide the locker keys, the specific account public keys, right up front. Because the system sees exactly which lockers are going to be opened before it even starts, it unleashes that whole army of clerks simultaneously. It deserializes the distinct sender and recipient blobs in parallel, updates the balances, and writes them right back. If 1,000 people are trading as long as they're using their own unique lockers, those clerks process them all at the exact same time. Section 6. Summary and next steps. Designing for performance. So, how do we actually use these blueprints to design for performance? Well, as an engineer, you've got 3 practical rules to live by here. Number 1, map out your hot, frequently updated fields to minimize contention. In the EVM, that means you've got to be really clever about your slot packing. In the SVM, it means splitting your data up across multiple accounts. Number 2, if you're building in the SVM, you absolutely must declare your accounts explicitly up front so the runtime can actually parallelize your work. And number 3, always separate your persistent state from your ephemeral state. You need that logical separation to properly manage your rollbacks and side effects. I want you to really let this quote sink in. Dense per-contract storage simplifies semantics. Many small accounts enable parallelism. That right there is the ultimate trade-off you have to master as a designer. The EVM filing cabinet makes your life a bit easier because the machine strictly enforces the rules. But hey, it heavily limits your speed. The SVM locker room. It gives you this incredible, sprawling parallel speed, but it puts the burden right back on you, the developer, to manage the data serialization and make sure you're passing the right keys.
And that is a wrap on our state overview. Next up in this module, we're going to cover state transitions and execution semantics. That's where we'll see exactly how these discrete reads and writes actually turn into committed changes through atomicity. To learn way more about this and to dive deeper into Web3 architecture, definitely head over to forge.college. Thanks so much for hanging out with me on this explainer brought to you by Forge College. I'm going to leave you with this final thought. If state really is the ultimate boss of performance, is your current smart contract architecture fighting the virtual machine or flowing with it? Something to think about. See you next time.